The Pacific Northwest Building Resilience Coalition is a gathering of organizations primarily in the cement, concrete, and masonry industries committed to furthering the planning, development, and construction of buildings and associated infrastructure better able to recover from and adapt to the growing impacts of an ever-changing urban and physical environment. Hello, my name's Brent Taylor. I'm going to be speaking with you today on behalf of the Pacific Northwest Building Resilience Coalition. I'm going to talk today about carbon sequestration in wood building products. But before we dive into this story, I'd like to briefly explain why it's gaining in importance. Why are we here talking about carbon sequestration in wood building products today? The built environment, which is the construction and operation of buildings, is responsible for more greenhouse gas emissions than any other sector, except for the oil and gas industry. This means that policies to mitigate the impacts of climate change must include a comprehensive plan to minimize the carbon footprint of the built environment. Increasingly, wood-based building products are being promoted as green alternatives to concrete and steel. And the argument is that while concrete or steel create carbon emissions, wood products actually sequester atmospheric carbon. There's been quite an effort to market the newer engineered wood products on this basis. But what I'm going to highlight today is that the full carbon impacts of wood-based building products are not fully accounted for in most studies and in the industry literature promoting these products. I'm going to start by laying out a few key messages for you here. First, it's a nearly universal assumption that timber is always harvested from a sustainably managed forest. But in reality, for a number of reasons, this is not always the case. At the point of harvest, when timber is removed from the forest, a significant amount of the already stored carbon is lost or emitted into the atmosphere. During the manufacturing process, again, there are significant emissions and losses of carbon. A lot of these emissions are not fully accounted for. Then, in the built environment itself, this issue of material selection is actually just the tip of the iceberg. Greening the built environment requires a much broader lens than materials substitution. The way the issue is often framed, that of wood versus concrete or concrete versus steel, is a bit of a misnomer, because in the final analysis it doesn't make a big impact on lifetime emissions. What does have a big impact are things like design, location, and longevity. The embodied carbon in these materials is only a small part of a much bigger picture. And finally, the carbon emissions associated with the disposal and landfilling of wood products are very poorly understood. We don't have a good handle on what happens to the carbon in wood products when they end up in municipal landfills. There's a great deal of speculation in what is really a crucial stage for carbon accounting purposes. I'm going to start by briefly covering the concept of carbon neutrality. Emissions from burning biomass or biofuels are called biogenic emissions. Now, carbon neutrality is the principle that when biomass is burned for energy, or the carbon from biomass is released into the atmosphere in some other way, these emissions are not counted towards the final carbon footprint of a product or process. The rationale behind this idea is that these emissions represent only the carbon that was initially absorbed by plants or trees while they were growing, and that these emissions will be fully reabsorbed by new growth later on. So this forms a hypothesis, the idea that biogenic emissions have a neutral climate impact. But currently, biogenic emissions are 100% exempt from final emissions figures, for instance on environmental product declarations. And what this means is that regardless of how many emissions a product or process is responsible for, as long as they're biogenic in origin, they aren't a part of the official carbon footprint of the product. On paper, they don't exist. And this accounting standard gives wood products manufacturers an advantage in carbon accounting because a large portion of the emissions associated with the production of wood products are biogenic. So carbon neutrality is in fact an accounting rule. It does not describe real-world emissions. Exempting biogenic emissions from the carbon footprint of a product on your balance sheet doesn't mean they don't exist. A carbon molecule from a biogenic source is identical to a carbon molecule from a fossil fuel source, and they have identical climate impacts. But one problem with this concept is timing. Emissions are immediate. Their greenhouse effects begin immediately, but it takes decades, or in some cases over a century, for new growth to reabsorb these emissions. But in reality, what we've done is emit a massive amount of carbon to the atmosphere and prevent that site from absorbing meaningful amounts of carbon anytime soon. Now, while the first generation answer to the question of biofuels was that they were 100% carbon neutral, there's a growing realization that this is not actually the case. Our current accounting rules for carbon neutrality were based much more on assumptions than on good evidence. So, for instance, a couple of years ago, the Science Advisory Board to the US EPA amended their initial position and declared that carbon neutrality can no longer be assumed for all biofuels. Some of the relevant questions that need to be asked include what type of wood is being burned? What's the species or age of the trees that we're talking about? Are whole logs being converted to fuel, or is it just branches, twigs, sawdust, and other residues? Is the wood sourced from a cool northern forest or a warm southern forest? Is the wood sourced from a commercial plantation, or has it been harvested from a natural, old-growth forest? Is the forest ecosystem suffering any degradation in quality as a result of repeated harvesting? And what type of fuel is being substituted for? This accounting framework also incentivizes the logging of forest land rather than the conservation of forest land, and this can be counterproductive. For instance, following the principle of carbon neutral accounting, there's no difference between leaving a healthy standing forest that sequesters a vast amount of carbon to mature or clear-cutting that forest and burning the wood for energy. On paper, these have identical carbon consequences, zero net emissions. Now, another concern that researchers have with the concept of carbon neutrality is that wood-based biofuels are just not very efficient. While there are differences between types of wood-based fuel or type of coal, for instance, in most cases, per unit of energy produced, burning wood or wood pellets actually emits more greenhouse gas emissions than any source of conventional fossil fuels. So there's a growing alarm that declaring all wood-based bioenergy to be carbon neutral will actually increase emissions in the air while decreasing them only on paper, because you need to burn a lot more wood to produce a small amount of energy. Now I'm going to break down the life cycle of wood-based building products into 5 distinct stages. The first one is forest management. Second is the point of harvest or logging operations. The third is timber manufacture, where harvested roundwood is converted to various forest-based products. And the fourth is the construction and use phase. This is where we're going to discuss the role of wood in the built environment itself. And finally, disposal, or end of life. So our story is going to begin in the woods. Forests are some of the Earth's most valuable carbon sinks. They're sometimes described as the lungs of our planet. Now, it's almost always assumed that lumber is being harvested from a sustainably managed forest. But unfortunately, from a carbon management perspective, not all forests are sustainably managed. In fact, what constitutes a sustainably managed forest is subject to much debate. The old-growth forests of the Pacific Northwest are some of the most productive carbon sinks anywhere on the planet. They can be thought of as vast reserves of carbon capital. And once this carbon is emitted or spent, it's gone. We typically think about wood as a renewable resource because, of course, trees grow back, but these old-growth forests are not a renewable resource by any definition. If you want to renew the carbon stock of a harvested 200-year-old tree, you need to wait 200 years. Now, one of the premises of sequestering carbon in wood-based building products is that from a climate perspective, mature trees are less valuable than younger trees. It's argued that they don't grow as fast or absorb carbon at as high a rate, but there's just not good evidence that this viewpoint is viable. Although the rate of growth will decline after a certain age, the absolute quantity of carbon uptake often continues to increase, and this is because a smaller percent in growth in a massive tree adds a lot more biomass than a large rate of growth in a small tree. And so even very mature stands, well over 100 years old, continue to act as net sinks of carbon. In the Pacific Northwest, rotation periods, which are the years between harvests, can sometimes be as short as 25 or 30 years. And while this can be highly economical, it has minimal value from a carbon management perspective. So unfortunately, there's a disconnect between rotation lengths that are good for carbon management and rotation lengths that are economically preferred. Now we're going to talk about some of the effects of logging on forest carbon. Now, so far we've only been talking about carbon in the trees themselves, but carbon is actually stored in the forest ecosystem in 5 different carbon pools. This data here from the US EPA shows that soil organic carbon is by far the largest carbon pool in the forest. On average, it accounts for about 50% of total forest carbon across the United States. The carbon stored in the merchantable portion of trees is only a small fraction of total ecosystem carbon. And so in order to account for the full impacts of transferring carbon from forests to the built environment, clearly a much more comprehensive view of forest carbon is needed. Most of the studies on carbon sequestration in wood products omit the disruptive effects of logging on the soil carbon pool, which, as we saw, is the largest pool in the forest, despite current evidence that harvesting reduces the level of carbon in the soil. These are effectively emissions from the soil to the atmosphere. During a harvest, only a portion of each tree is removed from the forest for processing. A significant portion of the biomass in the initial living tree is not merchantable. It has no economic value, and it's either left in the forest to decompose or is burned. These emissions also typically go unaccounted for. Because of the far greater carbon storage capacity of old-growth forests, harvesting these stands incurs an enormous and irreversible loss of carbon capital. The rate of reabsorption of atmospheric carbon after harvesting an old-growth forest is shown here. After 50 years of regrowth, only 38% of the carbon stored in the primary forest will be reabsorbed. After 75 years, 44% of the carbon is reabsorbed. And even after 100 years of regrowth, the secondary forest still only stores a little more than half of the carbon that was once sequestered by the primary forest. Now, current forest management practices mean that reforested acreage in commercial plantations will never reach the level of carbon sequestration attained by old-growth or primary forests. So taking this into account, a complete review of the carbon data that includes these terrestrial impacts can show that there's actually a carbon debt in existing wood products and structures. While living trees sequester carbon, wood products are the result of an industrial process that emits carbon. And these emissions occur at each of the 5 stages that we identified earlier. First, emissions from collateral damage to other carbon pools in the forest ecosystem during harvesting, emissions during the manufacturing process, losses during the construction process, as well as maintenance and replacement costs during the use phase, and at end of life when they're eventually disposed of. We're going to look at emissions during the manufacturing stage now. At the primary manufacturing stage, only about 40 to 50% of large roundwood logs are converted to lumber. The remainder, called mill residues, are burned for energy to power the mill or sold to pulp and paper plants for use in products with little to no long-term carbon storage value. These emissions from wood waste and wood fuel are of course deemed carbon neutral and omitted from the final emissions footprint of the mill's operations. Here's an example of the carbon neutral emissions from large facilities emitters in Washington. This chart breaks down emissions between fossil fuel and biogenic sources. As you can see, virtually all of the emissions, about 96% of them from Washington mills, come from burning wood-based fuel. Well over 1 million metric tons of greenhouse gas emissions get written off of these carbon balance sheets. These emissions that are omitted from final figures are equivalent to burning nearly 1.3 billion pounds of coal based on the EPA's greenhouse gas equivalency calculator. And while new growth may eventually reabsorb some or even most of these emissions, the process will take decades or even a century or more. In the interim, the greenhouse effect of these emissions are every bit as real as those from fossil fuels. This chart shows the outputs from primary manufacturing facilities in Oregon. Approximately 39% of the logs that enter primary manufacturing facilities are converted to lumber, 8% to veneer, and 9% are sent directly for pulp, paper, and board production. Now 44% of the biomass that enters the mills ends up as residue. and these residues are typically either burned for energy or sold to pulp and paper plants for the manufacture of other short-lived products. Now, while there are serious efforts underway to grow the market for mill residues, the options don't allow for much long-term carbon storage. So now that we have a more complete picture of the emissions and carbon costs associated with the sourcing and manufacturing of wood products, we're going to talk about the role that a given material plays in the overall carbon footprint of the built environment. The reality is that the carbon footprint of the built environment goes well beyond carbon accounting for specific building materials. The energy and emissions associated with all the processes and materials from their sourcing to the completed construction of a building are called the initial embodied energy of a building. And initial embodied energy accounts for somewhere between 10 and 20% of a building's lifetime emissions. So when we're talking about substituting one material for another, we're really only talking about an attempt to address 10 to 20% of the issue. This is only the tip of the iceberg. Discussions of carbon sequestration often frame the issue as one between hypothetical wood buildings and concrete or steel buildings. But in the real world, there are practically no such structures, those built exclusively out of one material type, that is. All buildings are constructed with a mix of materials. A single building may contain 60 different basic materials and over 2,000 different components. Each of these have their own embodied energy, costs, and longevity. In reality, all building materials are indispensable. If we're going to get serious about reducing the carbon footprint of the built environment, our attention and resources are much better spent on building better buildings. What proposals for carbon sequestration in wood products deal with is a much more narrow issue. It's material selection, and there are many factors to consider in this process in addition to initial embodied energy. For instance, durability, thermal mass, fire performance, moisture resistance, acoustics, cost, adaptability, resilience, and other factors are all considered when selecting a material for a particular building component. Because there are all these attributes to consider, each material has unique benefits and unique drawbacks, and design decisions therefore always involve a series of complex trade-offs. The initial carbon footprint of a given material is only one factor that needs to be considered in this process. And just as choosing the least expensive material is not necessarily the best option for a particular component, neither is simply choosing the material with the assumed lowest initial embodied energy. While the initial embodied energy of a building accounts for 10 to 20% of lifetime emissions, operating emissions, the energy needed to heat, cool, and power the building, account for 80 to 90% of lifetime emissions. In a full life cycle assessment, from the sourcing of raw materials to the decommissioning of a structure, the differences between material types in terms of lifetime emissions are marginal. It's a small part of a much bigger picture. The factors that primarily influence the lifetime emissions of a building are design, which in part determines the operating efficiency of the structure, location, orientation, the electricity source for the building, the climate, which dictates heating and cooling needs, the cumulative repair and maintenance required on your components, and the longevity of the building and its structure. Over the service life of a building, the emissions associated with the maintenance and repair of building components can actually exceed the emissions from their initial embodied energy. A highly effective way to reduce the contribution of initial embodied energy to lifetime emissions is to ensure the longevity of the structure. Building for resilience is important, and this is part of the bigger picture that I'm emphasizing, that of building better buildings. The last stage in the wood product's life cycle is disposal, and there are a variety of disposal options for wood products. The most beneficial from a climate perspective is recycling or reuse. Wood products can also be burned as a waste disposal option, sometimes to generate energy. And the third option is burial in a landfill. Currently, far too much wood waste ends up in a municipal landfill, and from a carbon accounting perspective, this is highly problematic. Under anaerobic conditions, wood and other organics are subject to decomposition by methane-producing bacteria. In this process, the carbon is converted to approximately equal parts carbon dioxide and methane gas. Methane has a 100-year global warming potential of 28 to 34 times that of CO2. And rising methane emissions from solid waste disposal sites are a serious and growing global problem. Now, the concern with wood products in landfills is that we don't really know how much methane they're going to ultimately produce. For instance, how much of the carbon in the wood is eventually converted to carbon dioxide and methane. And secondly, how much of this methane actually escapes the landfill? How much is recoverable with cap and flaring systems? As it stands, there are some laboratory models that estimate methane emissions from wood products, but the differences in these estimates based on the different models ranges tremendously, by well over an order of magnitude. Now, one thing to consider is that because of the damp and wet climate conditions in the Pacific Northwest, wood products can be expected to decay more rapidly. This means that results from studies conducted under different or drier conditions may not necessarily apply here. When it comes to the final fate of wood products in landfills and their ultimate carbon footprint, we just don't know enough to draw firm conclusions. So in closing, this flowchart is going to help us follow the carbon through the wood product's life cycle and summarize the key takeaways. At each step in the process, wood products are responsible for emissions even if they're not always accounted for. So in the final analysis, a number of researchers have tracked the flow of carbon from forest to finished product. And studies show that about 15 to 30% of the carbon that was once stored in the living tree ends up in a long-lived building product. So the transfer of carbon from the forest ecosystem to the built environment is just not very efficient. This process causes carbon emissions from a number of other carbon pools that are not always accounted for. For instance, the irreversible loss of old-growth carbon capital, carbon emissions from soil pools caused by logging, the potential rise in real emissions from the use of wood-based biofuels, and the vast uncertainty in final methane emissions from these products in landfills. At the end of the day, what we can safely say when we talk about carbon sequestration is that living trees sequester carbon, and wood-based building products are the result of an industrial process that emit carbon. A more realistic and comprehensive approach to greening the built environment is one that's less concerned with material substitution, and rather one that emphasizes building more resilient and more energy-efficient buildings. For more information, please visit www.buildingresiliencecoalition.org.